carry your book along. I know the book's heavy, the book's expensive. If you leave it in the room, it's going to be stolen. But it's a good idea to card it with you, or at least at a minimum, my notes ahead of time. But be sure you read the stuff from the text, because I may have shortened it a little bit, and you've got to be able to read the whole thing. Okay, you look at that. If this were a test question, people go, oh my God, there's 3 lines here I've got to paw through and make some sense out of. But we're going to break it apart. And I've broken it apart here by I've drawn you pictures so you can visualize what's going on. Okay, we have 588 gram piece of iron. In other words, a hunk of metal, like your metal cylinders, just a little bit bigger. Okay, I've got this 588 gram piece of iron, and it's heated to 97.5. Okay, here's the picture. Here's the iron, and it's a hot piece of iron. I'm obviously not holding it in my hand. Okay, that's where those little test tube holders would be really good. Now, how'd you get it that hot? Well, you could have had an oven down in the lab, and we have laboratory ovens. Or you could have stuck it down in boiling water for a while and brought it out. So you got this hot piece of iron. Okay, that was the first sentence. I took that first sentence, I drew that little picture. Then, second sentence. It is then dropped into 247 grams of water, originally at 20.7. Okay, here sits this water. Here's a cup of it, beaker of it. I've got 247 grams of it, and it's sitting there about room temperature. Okay, so we got a hot piece of metal, you got some cool water. You're going to take that hot metal, you're going to drop it into the cool water, carefully, so it doesn't splash. Okay, now they're going to be together. After they've been together a little while, it's going to equilibrate, okay, because one is going to lose heat, the other's going to gain heat. Remember how I told you the cats sleep in bed with me? Heat flow. It goes from the hotter object to the cooler object. We are going to assume the life here is perfect. Now, you know, you're old enough to know life's not perfect, but we're going to assume life is perfect, that the heat lost by the hot metal is exactly the amount of heat gained by the cool water. Now, life isn't quite perfect because the cup could get in on the action a tiny bit. The air above could get in on the action. The thermometer we might have down in there could take up a little tiny bit, but it's a small amount, so we're going to disregard that. So heat loss is equal to heat gain, and we know the specific heat of water. It's a given. See, it's up there in your problem. I told you last time. You don't have to memorize this number. It will be given. In OWL, there's a button for tables. Hit that button, find what you need. Okay, what we are doing is we are pretending we cannot look up the specific heat of iron. Iron is so exotic, we can't find it on the tables. Okay, so here's another way to show this. What if we were graphing this? And we do this kind of thing in 1412. I'm going to plot degrees Celsius versus time. Okay, here sits the iron. Okay, it's at 97.5. Just go along flat, no change in temperature. Here's the water. I've got 2 temperature probes, one for the iron, one for this. Its temperature is just 20.7. And then very quickly, I'm going to put them together, maybe swirl it a little bit. They're going to equilibrate. After they've been added together, they both end up at this temperature. Yeah, Bruce?
How do you get the temperature of iron?
Okay. If you have an oven, and you set your oven at 97.5, and that piece of iron's been in there for an hour, even though we can't get a thermometer down inside the iron, it's a pretty good bet the temperature is the same as the oven if it's been in there long enough. Or if you have it down. That's a great question because, yeah, thermometers don't fit down into a hunk of iron, do they? The other thing is if you had it in boiling water, and you have a thermometer in your boiling water, you know, separate water from this, you know, that's like using an oven. If your piece of metal has been down in that boiling water for 10 minutes, it's a pretty good bet the temperature of the iron, clear through it, will be the same as the boiling water. So we get it indirectly. But that's a great, great point there. How do you find out what temperature it is? Okay, so do you remember your equations for heat? Okay, this is going to be the heat loss side. And I said heat lost is equal to heat gain. Now, the one and only problem we worked together before, I just used one of these. Because remember that problem on Tuesday? We had water. I was going to make tea. I've got about a cup of water. I'm going to take water at room temp, move it up to almost boiling, 90-something, and we've worked out how much heat that's going to cost you. Okay, same idea here. The iron's losing the heat, and the water's gaining the heat this time. So heat lost on this side is equal to heat gained on this side. In this case, the hot substance is the iron, the cool substance is the water. Okay, now that equation, what do we put in the first here? Russell, do you remember?
Mass.
Mass. Mass of what in this case?
Iron.
Give me a number.
588 grams.
588 grams. Okay, now, we don't know the specific heat of the iron. That's what we're trying to find out. So let's just call that X. Okay, then, the last place here. Nina, what do we do with it?
That was the difference,
Okay,
the change in heat.
okay, what did the iron experience? If you look at this plot, the iron started here, the iron goes to here. The iron never experiences the 20.7. It just, where did the iron start? What was the equilibration temperature, you know, after they lost, gained, and so forth? So Nina, can you tell me what the delta T is?
97.5.
Tell me more.
76.8.
76.8, and give me some units.
Celsius.
Okay, good. Everybody see where she gets that? The trouble spot for people is the delta T. And remember how we were going to talk, delta T is always the absolute value. You're coming down or you're going up, it doesn't matter, absolute value. Anybody have a question where you got it? Yeah, Liz?
Explain that to me again.
Nina, explain that.
Getting a different one. It's
Oh, I
supposed to be
just-
61.3.
Okay, they're disagreeing with your math, maybe? Okay. So did you maybe go here to here, Nina?
No, I took the difference.
Here to here.
No, the difference from 97.5 to 20.7.
Metal never got down that cool.
Oh, it did.
That's why Liz isn't agreeing with you. So Liz, what did you get?
I got 61.3. I did the 97.5 minus the 36.2.
Okay, great. I'm glad we have math police out there. I said the delta T is the most problematic part. That's why I like to draw you pictures. Where did the iron start? Where did the iron finish? It never got as low as the water. Okay? Now, let's go to the other side. In this first place, right here, Brittany, what do I want to put in here?
The mass of the water.
And how much is it?
247 grams.
247 grams. Okay, then in here, what do we put here, Meredith?
And that one, the 4.18
Okay, give me some units.
joules per gram.
Tell me more.
Oh, Celsius.
Per degree Celsius. Weird, weird units. But if you stop and think what they mean, I want to heat up water. Okay, it's going to cost me 4.18 joules for every gram for every degree. Okay, and then the last and the hardest part here, Tanya, what's that going to be? Do you remember what we put in the last? We put a delta T. Okay, how much is it? See, the water started here on the plot. The water ends here. So what's your delta T, Tanya?
15.5
15.5. And units, Tanya?
degrees Celsius.
Degrees Celsius. Is that what other folks got? Okay, great. Let's do a unit analysis here. We have grams here, grams there, cancel. What else is going to cancel? Sarah, what else is going to cancel?
The Celsius.
Okay, and
The Celsius.
Celsius up there. Okay, now, we just have to be careful with our math. Here's what I would recommend. The unknown is over here. We want it to stand alone. It's already up on the top, so we can leave it over there. Let's go ahead, multiply these through, okay, get an answer. Then, and keep this rolling. Multiply these three through, do not do any rounding at all, just keep it rolling on your calculator. Then, if you're slick on your calculator, bring these over one at a time. The answer you got here, divided by 588. That answer, divide by 61.3. If you're not that slick on your calculator, then I would recommend multiply that out and write it down. Multiply these two together and write it down. And then bring it across one time and divide by it. But do you see how our units are going to come out? Here's joules up on the top. Here's grams, degrees Celsius are going to end up on the bottom. And we want X. And let's see what we get. Get your final answer. Round to the correct number of sig figs here. And I want units for this. Russell, you ready to go for it?
0.444
Okay,
joules per gram Celsius.
excellent. And that is our specific heat of iron. Do you see how this could be a practical thing? Let's say you work for industry and people were getting away from using microwave ovens and they're just using their regular old stovetops. You're trying to come up with some new metal alloy that will conduct heat really, really well. You want a new metal alloy that has a really super low specific heat, so you put in a little heat and up zips the temperature. And so you made these various alloys by mixing two or more elements, metals, melt them down, mix them together, let them re-solidify, make your pot or pan out of it. But you could get the specific heat of that by this simple, inexpensive little experiment. Take a hot piece of the stuff, drop it into some cool water, solve for the specific heat of your brand new metal you've just made up. Yeah, Meredith?
I'm a little confused on one part. How do you get, why do you subtract from the 36.6?
Okay, the water started here, the water ends here. So the change for the water is here to here.
Okay.
The water never makes it up to here. See, these are two separate things you brought together. Water started here and it goes up. Iron starts here and it goes down, but only to the equilibration temperature.
Okay, that makes more sense.
Okay, Bruce.
And on the test, we're gonna need to memorize that equation. You won't have those. We'll have the joules,
Okay,
we won't have the
you're,
equation.
okay, I would highly recommend, if you like flashcards, okay, we've got the one for Fahrenheit to Celsius, that's an equation, need to know. When I go, need to know, very dramatically, that means that'd be good for a flashcard. And those 3 metric English things, that just have a list, either a sheet of paper or something, but I don't recommend you just sit down and flat out memorize them. I recommend you do enough problems so you think, oh yeah, that's the one I need.